Hi, in this lecture we are going to talk about one of the most important sorting algorithms, the merge sort. So, let's get started. Basically, what is merge sort? Merge sort is a divide and conquer algorithm that was invented by John von Neumann during the Second World War. Okay, it is a comparison-based algorithm with running time complexity ordo n log n, and this is what we have been discussing in one of the previous lectures, that comparison-based algorithms cannot do better than ordo n log n, so linear arithmetic running time. Okay, there are several algorithms, such as string sorting algorithms, that can reach ordo n linear time complexity or even sublinear time complexity, but those algorithms are not comparison-based ones. Okay, so merge sort is a comparison-based algorithm with ordo n log n running time. It is a stable sorting algorithm. It is not in place, which means that it does need some additional memory. And although heap sort has the same time bounds as merge sort, heap sort requires only theta1 auxiliary space instead of merge sort theta n space complexity. What does it mean theta n? That we cannot do any better than ordo n. We have to allocate a one-dimensional array with the size of the original array. We are going to see the concrete implementation. We are not able to do any better. So merge sort is not an in-place algorithm, which means that it needs some additional memory. What's very important, that usually efficient quicksort implementations outperform merge sort. So for example, as far as Java is concerned, it uses merge sort for sorting reference types and uses quicksort for sorting primitive types such as integers, characters, and so on. Merge sort is often the best choice for sorting a linked list. In this situation, it is relatively easy to implement a merge sort in such a way that it requires only theta1 extra space. Okay. So let's compare quicksort and merge sort. Quicksort is an in-place algorithm, so it does not need any additional memory. Merge sort, on the other hand, is not an in-place algorithm, so merge sort does need additional space. Quicksort is not a stable sorting algorithm, but merge sort is a stable sorting algorithm. Quicksort worst case running time can be quadratic, as slow as bubble sort, while on the other hand, merge sort has ordo n log n running time, so it is guaranteed that it's going to be fast. As you can see, again, there is a trade-off whether to use quicksort or merge sort. Quicksort is going to be in place, but it's not going to be stable. Quicksort is usually faster than merge sort, but in a worst case scenario, it can have quadratic running times. So again, it's quite common concerning algorithms and data structures that there is a trade-off what algorithms to use. Okay. So what is the merge sort algorithm? We have to divide the array into two subarrays recursively, and we have to sort these subarrays recursively with merge sort again. If there is only a single item left in the subarray, we consider it to be sorted by definition, and we have to merge the subarrays to get the final sorted array. This is why it is a typical divide and conquer algorithm. We keep splitting the given array into smaller and smaller subarrays until we bump into the situation that the given subarray contains only a single item. It's going to be the base case of the recursive method call because we consider it to be sorted by definition, and then we have to merge the subarrays in order to get the final sorted array. Okay. So what about the divide phase? We have an array 32, minus 12, 0, 3, 1, 12, 20. We have to divide the array. We call the sort method over and over again. At the beginning, we call the merge sort on the entire array, starting with the 0 index and the last index in the array. Then we generate the middle index in order to partition the array. The middle index is going to be the low index plus the high index divided by 2. In this case, 0 plus 6 divided by 2. So this is how we partition the array. It's going to be the pivot. And we are going to call this merge sort recursively on the left subarray and on the right subarray. This is why it is the divide and conquer algorithm. This is the divide part, okay. Then it's very important that we are going to merge the left and the right subarray recursively with merge sort. So we keep splitting this array again, and we are going to have a left subarray in the left subarray and the right subarray in the left subarray. Then we are going to call the merge sort again on the left subarray and the right subarray, and we bump into the situation that in this case, as you can see, the left subarray contains only a single item and the right subarray contains only a single item. So in this case, we consider these subarrays to be sorted. Okay. So after several recursive method calls, we end up with single items. We consider them to be sorted by default, so we keep merging these already sorted items. So basically this is the diagram as far as merge sort is concerned. We have the initial array, we keep splitting the array. This is why we have to generate the middle index, and we will have the left subarray and the right subarray. And then we are going to split the left subarray to a left subarray and the right subarray, and we are going to split the right subarray into a left subarray and the right subarray until we bump into the situation where there are single items. And then we keep merging these items, as you can see, in order to end up with the final result, basically the sorted one-dimensional array. So we have been discussing the divide phase. In the next lecture, we are going to talk about the conquer phase, how to merge these subarrays in order to get the final solution. Thanks for watching.